So what I have over here is a pendulum, and the pendulum bob is connected to a spring, and the pendulum is connected to the ceiling, and the spring is connected to the pendulum bob, and the pendulum is connected to the floor. And what I'm going to do is I'm going to pull aside the pendulum bob, and then I'm going to release it. So initially the pendulum is at its equilibrium position right here in this red line. It's at its equilibrium position. And then after that, I'm going to pull aside the pendulum bob to an angle of theta. And then I'm going to, after releasing the pendulum bob, it's going to pass through its equilibrium position. And what I want to find out is I want to find the speed of the pendulum bob as it passes through its equilibrium position, shown in the circle, in the red circle. So I'm going to pull aside the pendulum bob, and then I'm going to release it, and I want to find the speed of the pendulum bob at its equilibrium position in terms of the given variables. So let's label some points on our diagram in order so that we can reference later. Let's say that when we pull aside the pendulum bob to an angle of theta, let's say that position at which the pendulum is at, let's call that position 0.1. And that's when we pull aside the pendulum bob from equilibrium. And let's say when we release the pendulum bob, and when it reaches its equilibrium position, let's call that position 0.2. So we want to find an expression, or we want to obtain an expression for the speed of the pendulum as at equilibrium, or at an angle of 0 degrees, which is at its equilibrium position. So the thing to notice here is that this is just a conservation of energy problem. Because when we pull back the spring, when we pull back the pendulum to 0.1, it gains a certain amount of energy. And when the pendulum is released and passes to 0.2, all of that energy from 0.1 is transferred into energy at 0.2. So all of the energy in the pendulum bob at 0.1 equals all of the energy of the pendulum bob at 0.2. So energy remains constant, or in other words, energy is conserved. So we can write a conservation of energy statement that the pendulum's energy at 0.1 equals the pendulum's energy at 0.2. And then now let's analyze what energy the pendulum bob gains at position 1. So when we pull back the pendulum bob to an angle of theta to 0.1, the pendulum bob gains a certain amount of potential energy because we are raising the pendulum bob to a position higher than its initial equilibrium position. And also, since we are stretching the spring from its equilibrium position, the spring is also being stretched. So the pendulum bob also has spring potential energy because we are stretching the spring. And so let's write down a potential equals 0 line. And this dashed line I just drew, that's the potential equals 0 line. And so what this means is that this is the line at which the potential energy of the pendulum equals 0. So any time that the pendulum passes through this dashed line in red that I just drew, at that point, the potential energy of the pendulum equals 0. So since at point 1, we are raising the pendulum bob to a point that's higher than the potential equals 0 line, or in other words, since point 1 is higher than the potential equals 0 line, that means that the pendulum gains potential energy. So we can write that the energy of the pendulum at point 1 that it has potential energy, which I'll denote with a capital U subscript G. And since we're also stretching the spring, it'll also have potential or spring potential energy. And so initially, when the spring is in its unstretched position, it looks like this. It stands vertically upward, and it has a length of L divided by 2, and that's its unstretched position, or its equilibrium position, because it's at rest and there's no stretching of the spring, or the spring isn't stretched. And the length of it is just, the unstretched length of it is just L divided by 2. But when we pull back, or when we pull aside the pendulum, we're stretching the spring from its equilibrium position, so it'll also gain spring potential energy. And now we have the two energies of the pendulum at point 1. Now, what energy does the pendulum have at point 2? So, when we pull aside the pendulum and when we release it, all of that energy at point 1 is converted into energy at point 2. And notice at point 2, it passes through the potential equals 0 line. So the potential energy of the pendulum is 0 at point 2. So it has no potential energy. But instead, since we are releasing the pendulum bob, all of its energy at point 1 is converted into kinetic energy, since it's in motion. And that's what we want to find. We want to find the speed of the pendulum at point 2. So the pendulum has only kinetic energy at point 2. Now let's expand these equations. The formula for the potential energy of the pendulum bob is just the mass of the bob times the acceleration due to gravity times the height the bob or the height the pendulum is from the potential equals zero line. And we'll later draw H on our diagram so we can see what it looks like. And so over here, this distance right here is the distance or the vertical distance that the pendulum bob or the pendulum is from its potential equals zero line. So this vertical distance right here shows how high above the zero line the pendulum bob is when it's pulled aside to 0.1. And so this value right here, that distance is the value of H. And the formula for the spring potential energy is just 1/2 times the spring constant times x squared. And x squared is how far we are stretching the spring from its equilibrium position. So when we stretch the spring, we're stretching it a certain distance, and that's the value of x. And all of that is equal to 1/2 times the speed of the pendulum bob squared. And the speed v is what we want to find. However, in order to solve for the speed, which is v, notice how there are other variables in our equation that are not in terms of our given variables, which are h and x. So on our diagram, the variables h and x, we would have to come up with alternative expressions for these variables in terms of our given variables. So the variable h isn't a given variable, so we would have to derive that equation or derive an expression for that variable. And the variable x is also not defined in our expression or in our diagram. So we would also have to come up with different expressions for those two variables, and then we would plug those variables in to our equation, and then we could solve for v. So let's first find the value of h in terms of our given variables. So here's the pendulum here when I pull back the pendulum. And here's the pendulum when it's at its equilibrium position, which is in the dotted lines. And here's the angle theta. And here's the potential equals zero line. And that's where the potential energy of the pendulum bob is zero. Now what is the value of h? The value of h is just how far above the potential equals zero line is the pendulum bob. When I pull aside the pendulum bob, how far is it from the potential equals zero line? And that's the value of h on our diagram. And let's get it in terms of our other variables. So we know that the length of the pendulum string when it's at its equilibrium position is just given by our variable L. And we know that if we draw a triangle, we know that this, when we pull aside the pendulum, we know that this length right here is just L because it's just the same string, but we're just pulling it aside. So the length of the hypotenuse of this triangle, of this small triangle we just drew, is L. And what would be the length of this side in terms of L and theta? We would have to use a trigonometric function. So this length right here, notice how this side of the triangle is just the adjacent side to the angle, and the adjacent side to the angle, we would have to use the function cosine of theta, and that side of the triangle would be equal to cosine of theta. Now why cosine of theta? Because the cosine of theta is equal to the adjacent side over the adjacent side of the triangle over the hypotenuse of the triangle. Now, what's the adjacent side to the triangle? The adjacent side is the side that we want to find, or the adjacent side is the side that we want to come up with an expression for. That's this line right here. That's the adjacent side to the triangle. Let's just denote that side with the letter A. And the hypotenuse is just L, which is just the length of the string. And so since we're solving for the adjacent side, or we're solving for the value of A, let's just multiply both sides by L, and then we can isolate A. So we notice that the adjacent side is equal to L times the cosine of theta, which is this length right here, L cosine theta. So that's the adjacent side to the triangle. Now notice here, we want to come up with an expression for the value of h in terms of L and theta. Notice here that the difference between L and L times the cosine of theta gives us the value of h. So if we just subtract these two values, we would get the value of h. So since we're solving for the value of h, we can just take the difference between L and L cosine theta. If we did that, we would get that h is equal to L minus L cosine theta. That's how far the pendulum bob is from its potential equals 0 line. That's the vertical distance the pendulum bob is from the 0 line. So now we have come up with a value of h in terms of our given variables. Now the variable that we need to find is x. X represents, so initially the pendulum is at its equilibrium position, but now since we're stretching the spring from the equilibrium position, we have to come up with an alternative expression for x in terms of our given variables. So let's draw a larger diagram in order to find the value of x. So here's how the spring looks like when I stretch it from its equilibrium position. So this length right here is still L, which is just the length of the pendulum string. This value right here is also a given variable because that's just how what the length of the spring is in its natural unstretched position. But now when we pull aside the pendulum bob to a different position, we're stretching the spring to a value that is greater than L divided by 2. And so the variable x would have to be drawn on this diagram. So when we stretch it, we're stretching in a distance x, and the rest of the distance is just L divided by 2. So the stretched distance is x, and the natural distance, or the natural unstretched distance, is L divided by 2. Now, notice here that we can draw a triangle. This side of the triangle is just L. And this side of the triangle is just L plus L divided by 2. And L plus L divided by 2 is just 3L divided by 2. This side right here is just x plus L divided by 2. And we want to solve for the value of x. And so our angle is still theta as it's shown in our original diagram. So the angle in our triangle that's given is this angle right here, theta. So notice that we have three sides of our triangle. We have L, 3L divided by 2, and x plus L divided by 2. So we need to come up with an expression for the value of x. Now the only way to solve for this is that we have three sides of our triangle and we have one given angle. In order to solve for x, we would have to use a law in geometry known as the law of cosines. And what the law of cosines states is that if we have a triangle, like the triangle we drew earlier, let's say one side is A, the other side is B, and the other side is C. And let's say that the given angle is a capital A, and the angle A is opposite to the side of side A, and let's say the other angle is capital B, and the other angle is capital C. And each of these angles are opposite to the letters of the sides that they correspond to. Let's say that we want to solve for side A. That side is just equal to A squared, which is equal to B squared plus C squared minus 2 times the length of side B times C times the cosine of the angle that's opposite to the side of A, which is capital A. Now let's apply the law of cosines to this earlier triangle that we drew. Because now we have these two triangles that we drew, we can apply the law of cosines to the triangle in order to solve for the variable x in terms of our other given variables. So which side does this side correspond to? So in our triangle, in the lower triangle, in the bottom left side, the side x plus L divided by 2 corresponds to side A. The side L corresponds to side B, and the side 3L divided by 2 corresponds to side C. So now we have three sides of our triangle. So now we can just apply this formula right here to this triangle over here. So we have side A squared, which is just x plus L divided by 2 squared, and that equals B squared plus length C squared. And that's minus 2 times the length of B times C times the cosine of angle A, which corresponds to theta. And angle theta is opposite to the side A. So now we're solving for the variable x. In order to solve for this, in order to isolate the variable x, notice how x is in a parentheses, which is squared. In order to isolate the x, we would have to take the square root of both sides in order to get rid of the square. If we take the square root of x plus L divided by 2, we just get x plus L divided by 2 without the square, and the right hand squared is just this. And notice how we can simplify this because 2 times 2 divided by a half is, those two will cancel out to give us 1, and L times L is just L squared. So we're left with 3L squared times the cosine of theta. Now let's bring in order to isolate x, we would have to bring the L divided by 2. We would have to subtract both sides by L divided by 2 in order to isolate for x. Now let's expand this out a little further. We can distribute the square into 3L divided by 2. And if we do that, we would get that 3 squared is 9, L squared is just L squared, and 2 squared is just 4. And so notice that each term has an L squared. So we can just, and so notice that each term has an L squared, so we can just factor out an L squared from each of the terms inside of the square root. If we factor out an L squared from the variable L squared divided by L squared is just 1. Factoring out an L squared from 9L squared divided by 4, we just get 9/4. And factoring out an L squared from the last term, we just get negative 3 cosine squared. Let's simplify this further. Notice that L squared is the variable that we factored out. We can take that out of the square root because L squared is a perfect square. So the square root of L squared is just L. And 1 plus 9 over 4, if we get a common denominator of 4, we get 13 divided by 4 minus 3 times the cosine of theta. And make sure you bring over the negative L over 2. And so this is the value of x, meaning this variable right here is how far the spring stretches from its equilibrium position when we pull back the pendulum. So this value right here just represents the stretched distance of the spring. Now we have our two values of x. And so the x right here just represents this very small stretched distance of the spring in terms of our given variables. So now we have our value of 8x and we have our value of h. Now let's substitute those in to our final, that are our earlier expression. And then let's solve for our variable v. So now let's just plug in our values of x and h into our earlier energy equation, and then let's just solve for the variable v. So first, before we plug in any values, let's just solve for the variable v, or the variable v squared. So if we multiply both sides by 2 and divide both sides by m, we can isolate the variable v squared. So multiplying both sides by 2, we get the following expression. And we're dividing both sides by m. Now let's simplify this down a bit further. We can distribute this 2 inside of the parentheses, and then we can also divide each of the terms by the variable m. So if we divide mgh divided by m, we would get just gh times 2. And the 2 and the 1/2, 2 times 1/2 is just 1. And we get k divided by m x squared. That's what v squared is equal to. And we also have to take the square root of the end in order to isolate the variable v squared. So first let's plug in our values of h and x that we found earlier. If we plug in, and so notice here in our value of h, or in our expression for h, each of these variables has the variable L, so we can factor out a variable L. If we factor out a variable L, and then we can substitute in. Factoring out a variable L, we get the following. And if we wanted to make sure we did this correctly, we could just distribute the L back in to the parentheses, and we would get our original L minus L cosine theta. So that's how I know I did the factoring correctly. And let's plug in our value of x squared. So we would have to square this entire expression right here. And also notice that each of these variables, or each of the terms inside of x, have the variable L. So we can factor out the variable L from both of these equations, or both of these terms, in order to simplify things. And then at the end we would have to square the entire expression for x. So factoring out the variable L, we get the following. And then L factored from L divided by 2, we would get minus 1/2. And remember that this entire equation right here is squared. So let's simplify our value for v squared. And so let's distribute this square into each of the variables in each of the terms inside of the parentheses. L squared is just L squared, and everything inside of this parentheses we would also have to square. So the square is distributed into L and these other expression. and all of that is equal to v squared. So in order to isolate the v, in order to get rid of the square on the speed, we'd have to take the square root of both sides. And if we do that, we would get this simplified equation right here, because we got rid of the square on the speed v, and now this is our final expression for the speed of the pendulum bob at its equilibrium position. So this entire expression right here is just the expression for the speed of the pendulum bob when we pull it back to an angle of theta, and then when we release the pendulum bob and when it goes through its equilibrium position. This expression right here is just the value of the speed in terms of our given variables.